2:41 a.m., early spring. Somewhere near the southern front, a Russian air defense radar switches on. For weeks, that system had remained silent, hidden, mobile, protected. Tonight, it moves closer to the front line, tasked with one mission: stop the growing wave of low-cost drones that have begun slipping through Russian defenses almost every night. The radar emits a sharp pulse. A signature appears on the screen, then another, then several more. Less than 4 minutes later, a flash cuts through the darkness. The radar goes dark. What happened in those few minutes exposes one of the most dangerous contradictions in modern warfare. When advanced air defense systems are pushed forward to protect the battlefield, they also become some of the most vulnerable and valuable targets on it. Russia moved its most sophisticated shields closer to the fight, and in doing so, it may have revealed exactly how those shields can be broken. If a system designed to stop missiles can be neutralized by weapons costing a fraction of its price, what does that mean for the future of air defense and for the balance of power on today's battlefields? To understand why Russia pushed advanced air defense systems closer to the front, we need to step back and look at how the air war has evolved since the early phases of the conflict. At the start, Russian air defense doctrine followed a familiar model: layered systems positioned deep behind the front. Long-range platforms guarded strategic assets, while shorter-range systems protected bases and logistics hubs further back. The assumption was clear: threats would come from aircraft cruise missiles or ballistic trajectories detectable at distance. That assumption did not hold. As the war progressed, the battlefield filled with low-altitude, low-signature threats: FPV drones, loitering munitions, and improvised UAVs flying just meters above terrain. These systems bypassed traditional detection envelopes, striking fuel depots, ammunition warehouses, and command posts with increasing frequency. By late 2024, Russian rear area infrastructure was no longer rear at all. This forced a strategic shift. To protect supply routes, helicopter bases and forward command nodes, air defense units were redeployed closer to the front line, sometimes within artillery range. Sophisticated systems originally intended to counter aircraft and missiles were now tasked with stopping small, slow, and cheap drones. But this created a dilemma. Air defense systems rely on emissions. Radars must transmit to sea. The closer these systems move to contested zones, the more they must operate continuously, tracking, classifying, and engaging targets in crowded electromagnetic environments. Each radar pulse becomes a beacon announcing its position to anyone listening. And someone was listening. On the other side, Ukrainian forces and their partners had adapted. Satellite imagery, electronic surveillance, and open-source intelligence were fused to map air defense deployments with increasing precision. Patterns emerged when radars turned on: how long they stayed active, how often they relocated, and which assets they protected. The front line was no longer defined only by trenches and artillery. It extended into the electromagnetic spectrum. By moving advanced air defenses forward, Russia aimed to close gaps in its protection. Instead, it may have exposed the very systems holding its defensive network together. The stage was set not for a traditional airstrike, but for something far more asymmetric. Long before the first drone ever lifted off, the operation had already begun quietly, methodically, and far from the front. Intelligence gathering was no longer about spotting convoys or counting vehicles. It was about patterns. When did the radar turn on? For how long did it transmit continuously or in short bursts? Did it relocate after firing or stay in place? Commercial satellite imagery provided the first layer: subtle changes, fresh tire tracks disturbed soil, newly cleared patches near tree lines hinted at recent deployments. But satellites alone were not enough. The real breakthrough came from combining space-based observation with signals intelligence closer to the ground. Small electronic surveillance teams monitored the electromagnetic spectrum. Each radar emission had a fingerprint frequency, pulse repetition, power output. Over time, these signatures were cataloged and matched to specific air defense systems. When a familiar signal reappeared near the front, analysts already knew what it was and roughly where it came from. Meanwhile, reconnaissance drones flew cautiously, never directly toward the suspected site. Their task was not to attack, but to confirm. Flying low using terrain masking, they searched for supporting elements: power generators, antenna masts, vehicle silhouettes partially concealed by camouflage netting. Inside a dimly lit shelter several kilometers away, operators worked in near silence. Batteries were warmed under insulated covers. FPV drones assembled from commercial components were tested one last time. Cameras were checked, control links verified, backup frequencies prepared. There was no room for improvisation once the attack began. The plan relied on timing. The radar had to be active. Too early and the drones would find nothing. Too late, and the system might shut down or relocate. The window could be minutes or seconds. For the drone pilots, this was not abstract strategy. It was personal. Many had seen previous missions fail when targets disappeared at the last moment. Others had lost friends to air defense fire that came from systems like the one they were about to hunt. Tonight, everything depended on patience. They waited for the signal confirmation that the radar was transmitting again. When it came, there was no celebration, only a quiet acknowledgement. The operation moved from preparation to execution. The first drone launched without sound. It rose only a few meters above the ground, immediately slipping behind a low ridge line. Its electric motors produced no thermal plume, no roar, only a faint whine drowned out by the wind. On the operator's screen, the image was grainy, slightly distorted by interference, but usable. The radar was active. That was confirmed almost instantly. Electronic sensors detected steady emissions sweeping in a predictable arc. The air defense system was searching, confident, exposed. 2 more drones followed, each taking a different route. None flew directly toward the target. Instead, they moved laterally, skimming fields, tree lines, abandoned roads. From above, their paths would have looked hesitant. From the inside, it was deliberate. The air defense crew reacted quickly. On their screens, multiple low-speed contacts appeared, ambiguous, difficult to classify. Too slow for missiles, too small for aircraft. The system switched modes, attempting to filter clutter from terrain and vegetation. For a moment, the drone seemed to vanish. Then one reappeared. A burst of fire erupted from a short-range gun system. Tracer rounds carved glowing lines into the night sky, tearing through empty air just seconds after the drone had already dipped lower. The engagement was reactive, rushed. That was the opening. The drones were never meant to arrive together. They were staggered seconds apart to force the defense system into constant decision-making. Engage one target and another slipped through from a different angle. Inside the control shelter, operators leaned closer to their screens. The video feed shook violently as one drone passed through turbulence from nearby explosions. Static flared, then cleared. The target came into view, a rectangular radar array, elevated, rotating steadily. For the first time, the drone climbed. It rose just enough to clear a final line of trees. The radar filled the frame. At that moment, the air defense system detected the threat with certainty. Alerts triggered, weapons slewed, another burst of fire erupted closer this time, too late. The drone struck the radar array directly. The impact was immediate. A flash, sharp and white, followed by a shower of sparks. The radar stopped rotating. The screen in the control shelter went black, but the attack was not over. A second drone reached the site seconds later, aiming not for the radar itself, but for the support equipment nearby: generators, power cables, control units. It descended rapidly, correcting its path in the final meters. Another explosion. Flames spread unevenly, licking along the edges of camouflaged netting. Secondary detonations followed, small but unmistakable. Within moments, the radar site was silent. No emissions, no tracking, no engagement. From the perspective of the air defense crew, the loss was sudden and disorienting. A system designed to dominate the airspace had been neutralized in under 5 minutes without a single missile fired. From the attacker's side, there was no celebration. The operators immediately cut feeds, powered down equipment, and began relocating. They knew what would come next. Artillery, counterstrikes, search efforts. But the damage was done. A gap had opened in the defensive network, not because of overwhelming firepower, but because of precision timing and the ruthless logic of asymmetry. Advanced air defense had moved closer to the front, and the front had moved right back at it. The response came quickly, but not quickly enough. Within minutes of the radar's destruction, Russian forces initiated standard countermeasures. Nearby short-range air defense units switched to heightened alert. Artillery batteries were tasked with suppressing likely launch zones. Electronic warfare systems began flooding the area with noise, attempting to sever control links and disrupt any remaining drones. But the attackers were already gone. This is one of the central challenges of countering small UAV operations. Unlike aircraft or missile platforms, drone teams leave little behind. No runway, no heat signature, no fixed position to strike back at with certainty. By the time counter-battery fire arrived, the launch sites were empty. Air defense doctrine assumes a second chance. If one interceptor misses, another can be launched. If one radar is jammed, another can take over. But when a radar is physically destroyed, there is no redundancy in the moment, only a blind spot. Temporary measures followed. Nearby systems attempted to extend their coverage, operating at higher power and longer duty cycles. This, however, increased their own exposure. Each additional radar emission expanded the electromagnetic footprint, making detection easier for anyone watching. In theory, layered defense should absorb losses. In practice, the loss of a forward-deployed radar forces commanders into difficult decisions: pull systems back and accept gaps, or keep them forward and risk further strikes. Neither option is ideal. The defensive response highlighted a growing reality. Air defense can no longer rely solely on interception. It must anticipate attack, minimize emissions, relocate constantly, and accept that some threats will get through. The engagement ended not with a decisive counterstrike, but with uncertainty. And uncertainty in modern warfare can be just as damaging as physical destruction. At first glance, the outcome seems counterintuitive. How could a modern air defense system designed to counter aircraft, cruise missiles, even ballistic threats fail against small, improvised drones? The answer lies in a mismatch between design assumptions and battlefield reality. Most advanced air defense radars are optimized for speed and altitude. They excel at detecting fast-moving objects with clear Doppler signatures: jets, missiles, high-flying UAVs. Small FPV drones operate at the opposite end of the spectrum. They fly low, slow, and close to terrain, blending into ground clutter that radars are programmed to ignore. To detect them reliably, radar sensitivity must be increased, but higher sensitivity comes at a cost. False positives multiply, processing loads increase, and most importantly, the radar must transmit more frequently and at higher power, making it easier to locate. This creates a paradox. The better the radar tries to see small drones, the more visible it becomes itself. Missiles are another problem. Launching a surface-to-air missile against a drone costing a few $100s is economically unsustainable. Even short-range interceptors are orders of magnitude more expensive than their targets. Commanders hesitate, delay, or attempt gun-based solutions instead, often too late. Electronic warfare offers limited relief. While jamming can disrupt control links, many FPV drones operate with frequency-hopping protocols or pre-programmed guidance for the final attack phase. Once close enough, they may not need continuous control at all. Then there is reaction time. A drone flying at low altitude may only be detected seconds before impact. By the time the system classifies the threat, slews weapons, and authorizes engagement, the window has nearly closed. Against a swarm or even staggered single drones, this timeline collapses entirely. Finally, forward deployment magnifies every weakness. Closer to the front, air defense systems face constant pressure, artillery range, counter-battery fire, reconnaissance drones overhead. Mobility becomes constrained. Emissions discipline erodes under operational demand. Systems stay active longer than doctrine recommends because commanders fear what they cannot see. In this engagement, the defense did not fail because it was obsolete. It failed because it was forced to perform a role it was never truly designed for. The lesson is not that air defense is irrelevant, but that its future will depend on adaptation, integration, and acceptance of limits. And those limits are being tested every night. The destruction of a single forward-deployed air defense radar does not by itself decide a war, but its impact ripples far beyond the immediate site. In the short term, the loss created a localized gap in coverage. Helicopter operations were delayed. Supply convoys altered routes. Reconnaissance flights were reduced or rerouted. Even temporary blind spots forced cautious behavior, slowing tempo and complicating coordination across the front. More importantly, the psychological effect was immediate. Air defense units are meant to provide reassurance to commanders, to pilots, to troops on the ground. When those systems are shown to be vulnerable, confidence erodes. Crews become more hesitant to activate radars. Commanders hesitate before moving systems forward again. Every decision becomes a trade-off between visibility and survivability. At the operational level, this pushes a shift in doctrine. Systems once concentrated for maximum coverage must now be dispersed. Mobility and concealment begin to outweigh raw detection range. Defensive planning becomes less about dominance and more about resilience. The broader consequences extend beyond this battlefield. Militaries around the world are watching closely. The cost asymmetry on display: cheap drones neutralizing high-end systems raises uncomfortable questions. Procurement priorities, training models, and even export strategies are being reassessed. For states that rely heavily on advanced air defense to protect critical infrastructure, the implications are stark. No system can be everywhere. No radar can stay silent and effective at the same time. And no defense, however sophisticated, is immune to adaptation by a determined adversary. This engagement illustrates a turning point not in technology but in mindset. The air is no longer dominated solely by those with the most expensive tools. It is contested by those who learn fastest. And that contest is far from over. This engagement offers a clear, sobering message about the direction of modern warfare. Russia moved advanced air defense systems closer to the front to solve an urgent problem protecting forces and infrastructure from an expanding drone threat. That decision was logical, even necessary, but it also exposed a fundamental vulnerability, one that technology alone cannot easily fix. Air defense remains essential. It deters, disrupts, and limits freedom of action in the air. Yet this case shows that dominance no longer comes from hardware alone. It comes from how systems are used, how quickly tactics adapt, and how well commanders understand the trade-offs they face. Radars must see, but seeing reveals. Missiles can intercept, but at unsustainable cost. Silence preserves survivability, but creates blindness. There's no perfect balance. What emerged instead was a new reality: asymmetric pressure applied continuously. Small teams, inexpensive tools, and precise intelligence forced a high-value system into a position where any choice carried risk. That is not a failure of engineering, it is the nature of a battlefield shaped by rapid innovation. For militaries worldwide, the lesson is not to abandon air defense, but to rethink it. Integration with passive sensors, greater emphasis on mobility, layered low-cost countermeasures, and realistic expectations of coverage will define the next phase of adaptation. Wars are no longer decided only by who possesses the most advanced systems, but by who understands their limits fastest. In that sense, this was not just an attack on a radar site, it was a test of doctrine, assumptions, and strategic flexibility. And those tests are happening every night. Bye for now.